Yeah. If not, it's fine. Yeah.
You should start one word.
Oh, okay.
We'll bring some. All right, welcome everyone. So today we have the first seminar of the spring semester, and we have a semi-local visitor from UIUC, Zhencheng Wang. Is that my
Zhencheng.
Zhencheng Wang. I'm sorry about that. And he will tell us about type 1 von Neumann algebras from gravitational path integrals. Please.
Okay. So hi everyone. I'm Zhencheng from UIUC. So thank you very much for the invitation to give the first talk of this semester. So today I'm going to talk about some work that I did with these people. It came out like 3 months ago. It's about getting von Neumann algebras from gravitational path network. So what are the motivations for old-fashioned. Okay, that's nice. Okay, so in this talk I will give an introduction to construction of Hilbert spaces and algebras defined by gravitational path integrals, and the kind of.
Can you talk a little louder, just to make
sure. Yeah. Okay. Yeah. So with this kind of algebra and Hilbert spaces we constructed, where we can understand the following questions better. So the first is that what's the interpretation of the Takanagi surface, which computes some entanglement entropy, like in the some boundary CFT region in the ADS-CFT setup, but purely based on the bulk Hilbert space without reference the ADS-CFT correspondence. And the other thing maybe we can also try to answer is that recently there are some work about type 2 von Neumann algebras in the semi-classical limit, and they also compute entropy from these works. And how does the non-perturbative effects affect these kind of results? Okay, and the result we get will actually be very general. Actually, we can maybe interpret it as in some other, just quantum field theory setup, not necessarily gravity, because they are only based on several axioms for path integral, which we'll explain later. And the plan for today is to first talk about these axioms, and then describe the algebras and Hilbert spaces we'll construct from path integrals. And then I'll get to this type 1 von Neumann algebra and what it tells us. And then I'll go some examples and finally some summary. Okay, so what is Euclidean path integral, or gravitational path integral that we are considering? So setup is kind of like this. Suppose we have some UV complete bulk theory. Okay, that maybe some clever people that give us that contains something we can call Euclidean path integral, where you only need to know the boundary condition on some closed manifold, which we call M. And it doesn't matter if this is actually a sum over geometries, like something like this. Okay. In general, you do some kind of integral in some higher dimensions. Let's say fill in the bulk here. And what we really need is just a map from these boundary conditions to a number. And these boundary conditions we'll call source manifolds, because in general you can put source for the fields on it. Yeah, so we should call it. So this map is some zeta of M. We just need this map. And the boundary condition specifies the boundary metric, and as well as boundary conditions for other fields. I mean, you can imagine ADS-CFT, you have metric and other matter fields, and then these are you have some boundary condition for that, and you iterate the bulk in some higher dimension. Okay. Right. So here are our axioms. Okay. What we want for this gravitational path integral. The first thing is finiteness. And this means that the map I just described is finite. So here I use XD to denote the space of d-dimensional smooth closed source manifolds. And we can also extend this map to the formal linear combinations of these manifolds. Just extend it linearly. Yeah.
It's not just a manifold. You're prescribing M with all sorts of local data,
Yes.
right?
Yes.
So it's not just a manifold. And what do you mean by saying XD is a d-dimensional small closed source manifold?
Right, that's what you said. It's a manifold equipped with metric and also the matter data for matter field.
So this is a vector space? You want to think of it as a vector space?
You mean X? Yeah, X, yes.
The space of these.
Right.
Okay. There's some sort of
Yeah, you can, you can define some kind of formal linear combination of these things, right? And for some space, right? Okay. And then, the second thing is reality. We want this path integral function satisfy path integral map satisfy this condition. When you conjugate all the sources on the manifold M, the answer you get also get conjugated. Okay. And the third one is reflection positivity, because in many cases we want the path integral to define some kind of inner product. So when this source manifold or maybe linear combinations of source manifolds is invariant under reflection and also complex conjugation of the matter fields of all the fields, then we expect this to get a positive answer. Or okay, I think here I should put non-negative instead of positive because there are some null states here. Okay, so here is a picture showing that the reflection positivity condition can be imposed on some like formal linear combination of surfaces. So, for example, here we should expect this to give a non-negative answer for doing this path.
It needs to be understood that some sort of generalizations of the axioms of topological quantum field theory that's formulated in terms of just a boundary manifold, and like, but you're adding some sort of local data on the boundary manifold, supposedly.
Yeah, I mean, it doesn't need to be local, right? It's just some data on the boundary that yours. That's the boundary condition for you to do your bulk path integral. Okay. Yeah.
Question. So
Yeah.
reflection, usually reflection positivity have like so if you're just getting a path integral with a boundary condition, you get it normally take for example, if you had a lower half space, we get upper half space and we combine that, and that's positive.
Yeah.
So you shouldn't have you thinking about the norm as like size mod square instead of
Right.
die. If I'm computing in a product, there is the boundary condition, right? So, yes.
Yeah. So, for example, this thing is a boundary condition for you to compute some norm of some state psi.
Here, like two of them.
Yeah. So, for example, this is the bra and this is the cat. We can have just one single one of them. Here, I'm saying, okay, we can do this more generally. We can have the linear combination of these things.
No, but there you look like you have two,
What do you mean? I have two?
like VW. M is just one.
Right. So this is some linear combination of surfaces, right? And it has this reflection symmetry.
Maybe another way of asking, correct me if I'm wrong, when you, if M was just topology, then you would say I'm sewing these, but you have local data, you're saying that, let's say you have some boundary condition J1 on this side and J2 on the other side.
Mhm.
When you put these together, you're not integrating over J's. What is what's going on when you put them together?
Yeah, I don't integrate over the days. Well,
So how
we require the date, okay, so.
And literally multiply the numbers.
Okay, I think, okay, at this step, I'm only saying, okay, we have some axioms on the path integral on some closed manifolds, like manifolds like this. I haven't talked about like gluing
Okay.
things with you know, manifold with boundaries. Yeah, so okay, maybe I should, you really should interpret this picture in the other way. Like if I have this kind of thing, this is some combination of manifolds that satisfy this reflection symmetry. And then you can kind of interpret this as saying, okay, we have some, this is computing a norm of some state that is in this kind of way. Maybe it will be clear later. Okay. The fourth condition is that we require some continuity of this path integral. We don't require the full continuity under deformations of the surfaces. It turns out that only one kind of continuity is enough for us to derive our results. That is continuity under changing the length of the cylinder. So when your closed manifold contains a cylinder, which is like this, some lower dimensional manifold across some interval, and we require the map to be continuous in this length of cylinder for all epsilon.
What do these words mean? Do you confuse continuous in epsilon, but epsilon is a coordinate. We're talking about manifolds. Do you have a coordinate system in mind?
I mean,
What does it mean?
there's some metric on the manifold, right? That can.
But you didn't want to fix the metric. You just fix the boundary conditions on the surface. Not, are you going to fix the metric in an interval of the boundary condition?
No, I'm fixing the metric on all of this closed manifold because this is the boundary condition for the bulk path integral. So you want to fix the metric. So here I'm just talking about the boundary, right?
Yeah, I think in the previous picture, it was confusing that it looked like the red circle was the boundary, but the full thing is.
Oh, sorry. Yeah, maybe it's confusing. So these are all just the boundary manifold. Let's say bulk is D+1 dimensional. These are D-dimensional manifold. And I'm not talking about the bulk yet. So.
Got it.
Okay, maybe it's confusing. Yeah, so everything I said here is all about the boundary manifold.
This is also about the boundary.
Yes. So all in all of the axioms, I don't mention the bulk. I just say there are some bulk pathing we can do with this boundary data.
So for example, a block would be a solid picture like this,
Yes,
filling it in.
Yeah, correct.
For the moment, you don't have to have a path integral, it's just some function.
Just some number.
Yeah, some number, yes.
Just some number. I see.
Then can you go back to number 3? Because I was thinking in terms of computing a norm. But this is just your M has a reflection.
Yes, the boundary condition has some reflection.
And why does it have to be positive then?
Well, you would expect the bulk path integral also gives you some positive answer, right? If the boundary condition, let's say in ADS-CFT, if your CFT path integral is kind of reflection positive, and define some norm of some states, then you would expect the bulk path integral to also give the same things. Does it make sense? Okay.
Sorry, then I guess I just realized that then what is, oh, I see. What is M star? What was the definition of M star?
Oh, you conjugate all the sources on M, all the matter data.
Conjugate means complex conjugate?
Yeah,
So these
complex.
are complex sources.
Yeah, in general, could be complex sources. Hope it's clear. If you have any questions, you can ask me. All right. Yeah. So okay. This is you mentioned this continuity assumption. And the last thing I want to impose is the factorization axiom, which means if your boundary condition is a union of two compact closed manifolds, then you have this kind of factorization. Okay, so here are some comments. So the axioms hold if there's a dual CFT, let's say in the ADS-CFT setup. But the above axioms are actually much weaker than the full axioms of CFT, or even for a QFT. For CFT or QFT, you can just think of the path neighbors on these closed manifolds. But in terms of gravity, we're thinking of this as some boundary conditions and do the path neighbor in some higher dimension.
Can we go back to the previous slide?
Oh, sure.
You know, it's confusing.
Sure.
This factorization. Let's say my boundary has two disjoint circles.
Yeah.
This means that the number that you associate to these two boundaries as a path of gravitational path of or whatever it is just the number for this plus the number for that. That sort of like rules out the option for having wormholes between the two.
Right. I'm going to talk about this in a moment. Yeah. Yeah. So as Nima said, if you do a gravitational path neighbor, there are space-time wormholes that can connect these two boundaries and violate this factorization. But it turns out this factorization axiom is very important in what we will derive. So what's our way around this? So usually in this case, in these cases where factorization is violated, there's a story about the bulk path neighbor is due to some ensemble of theories, and in each member of this ensemble, we have this factorization. So the way around this is that we'll just work within a single member of the ensemble, and yeah, the rest of the story will just be in there.
Don't you think that this just already deviates from what gravity suggests?
Already deviates from what
Gravity tells you that you have these wormholes. Right? If you want to do like pure gravity, quantize pure gravity, and write down the Euclidean path integral of pure gravity. Right. It doesn't factorize.
Yes, but it has this kind of structure. Or maybe you can think of this as like maybe universe alpha states. Yeah, okay. Sure.
It seems like when you might get time for it's just because you're giving factorization. Is that fair to say?
I'm not sure because there are other things I need to assume for me to get a type 1. And also the path neighbor factorization might not be the same as Hilbert space factorization. Right. Here I just assume path neighbor factorization, but I think what we're getting is Hilbert space factorization. I'm not sure if it's directly related to each other. Yeah. So here,
but there is no way Hilbert spaces could factorization of path integral was proposed.
you say again?
So even though factorization is not like you need to assume more things, but if factorization was of path integral was violated, then I don't see a way to get factorization of Hilbert space. Is that fair to say?
Yeah. Maybe I'm not sure. Maybe I don't know if there are ways to prove that. yeah, I guess here you can maybe think of the quantum gravity Hilbert space as, you have some kind of super selection sectors, and in each sector you have this factorization, and we're just working one such sector. And
So like one universe reducible.
when, yeah, kind of. Right. Yeah, it would be great to include, to, remove this factorization axiom and see what we can get. So now I'll just construct the Hilbert space of states for here. So we want to construct Hilbert space states by cutting open the gravitational path interval. So we can imagine some setup like this, where this is you cut at some Cauchy slice in the bulk, and this is some cat is some bra here. And the inner product between any two such states is given by gluing these two manifolds along this boundary. And of course, the boundary data must match or do this gluing. And you get a closed manifold, and then you evaluate this path integral to get the inner product. However, this manifold might not be smooth, right? Because if you're gluing, there might be some kind of kink along this corner. And as a result, the answer you get might not be finite if you are integrating over, if you have some non-smooth manifold as your boundary condition. So we have a way to kind of avoid this kind of situation is to restrict the manifolds N1 and N2 to manifold through what we call rimmed manifolds. The rimmed manifolds just means that on the manifold N1 or N2 near the boundary B, the manifold looks like a cylinder, okay, in some neighborhood of the boundary B. And so when you do all kinds of gluing, you always end up with some rimmed manifold, with some smooth manifold. And it doesn't matter what value epsilon you take for this rim, as long as it is finite, everything is fine. Yeah.
What is meant by smooth here? You're not talking manifolds, you have local data. So you're saying that, for example, if you have metrics, you want not only the value of the metric to match on the boundary, but also the first derivative or something, some sort of like zero junction type of thing.
Yes.
Okay.
Yeah, here actually, because it's cylinder, all the derivatives vanish as you go to this. I mean, you can consider a situation where you relax this condition and you still get some smooth manifold.
Here, what you're describing is just like Euclidean path integral of the quantum field theory and how it makes sense of them usually. On the boundary, you're doing the same thing.
Yeah.
You have to also take a rim around that over there.
Right. Yeah, a lot of these things are similar to path integral in quantum field theory. But so what are the Hilbert spaces? One thing I need to mention is that we also assume points on the boundary are labeled, so we only have one way of gluing these two manifolds. For example, if there's symmetry, you might, let's say, for example, U1 symmetry or something, you can have multiple different ways of gluing these things, and we just want to avoid that kind of situation. So we say, okay, the points are labeled, and we only have one way of gluing, and each choice of this kind of boundary B defines a free Hilbert space with the positive semi-finite inner product, because we assume reflection positivity. So this is what you get, and then you can define the actual Hilbert space by quotienting the null space and do the completion with respect to this inner product. And for each choice of B, we can call this the B sector of the full quantum gravity Hilbert space. Right? There are other sectors with different boundaries, and right. So here, as long as this kind of this Cauchy slice has the same boundary, we are within this Hilbert space.
Sorry, which was, so one way to associate such numbers, manifolds, is by taking literally the Euclidean path integral over this boundary manifold of quantum field theory and this boundary manifold, right? So that would satisfy all the axioms that you have.
Yes, I agree. Yeah.
You would say that provides one example of you're still calling that the B sector of full quantum gravity space? Because there are many ways to satisfy it.
Sure. I agree.
Pure QFT is one example, but okay.
Yeah, you can, sure, you can say, okay, maybe it's the B sector of the QFT Hilbert space. Yeah, just imagining if you do quantum gravity, these might, it might be expected to satisfy these axioms. Right, so that's why we call it, quantum gravity Hilbert space, but QFT, I think it should also work. Okay. And so in our case, we'll only consider one special sector with one special choice of B, which is something like this. You have a union of two compact surfaces as your boundary B. And this is what we call a two-boundary sector. And we also choose a very special case where the two boundaries are the same. Okay, so just to remind you that this surface is a d-dimensional surface. This is the boundary of the bulk theory, and you're doing passing rule in the D+1 dimension. Okay, right. But one very special thing of this kind of surface is that it not only defines states, but also defines operators.
Just when you say you're doing a path integral, and because we're imagining it, right? You're associating numbers, but should we imagine some sort of an end of the world brain sitting on, because this is a boundary, right?
Yes.
You have to tell me what happens in the bulk inside that B of L.
Okay.
Are you imagining some end of the world brain? Are the degrees of freedom? Because even in QFT, there could be degrees of freedom on the boundaries, right?
Right. Yes. Here I'm kind of ignoring this issue because we only consider path integral when we have closed manifold. When we glue things together, do like inner product or something like that.
Before you glue, you have something with a boundary.
Right. And I'm not specifying anything in the bulk. I'm just specifying things on this surface.
There cannot be, you're assuming that there's no extra data associated with the boundary of the boundary manifold.
Yes, right. But I agree. There could be more structure if you.
Just on quantum gravity, you expect something like the whole brain or
Sure.
or the degrees of freedom involved.
Here I'm not considering that. Okay. And we right. Yeah. So these could be operators. Operators of algebra. Right, and we call the set of the linear combination, the set of linear combinations of these kind of surfaces, Y. Okay, and let's see how it can be defined as algebras first. Okay, so now we can formally define a surface algebra, which is these surfaces with some rule of multiplication. So, for example, we have the surface A and surface B. You can define left multiplication and right multiplication, just glue things in different order. Okay. And there, the two different algebras defined by different rules of multiplications are related by some antilinear isomorphism, which we call star here. This map is conjugating all the matter sources and switch the left and right label. So here, I should say that every manifold with two boundaries has I mean, the boundary has labels on it, which we call left and right,
I mean,
and use.
going by, yeah, the boundary of a boundary is supposed to be like zero, right? So this cannot be the boundary, right? It's other boundary like fields there, you know.
Yeah, okay. So okay, maybe I should just say, okay, this is so these red circles are boundaries of some manifold, right? We don't think about the bulk theory yet, right? When you glue all the boundary manifolds together to form a closed surface, and then maybe you can think of the bulk. I think we're there. So that's maybe, yeah, that's why I should call these source manifolds to avoid the abuse of the word boundary. Okay, so just in terms of the source manifold, we can do these kind of operations, and you can see that these two different algebras we define are related by this star map here. And on this surface algebra, we can define a map that we call trace. How it is defined? It's defined in this way, where you glue the two ends, the two boundaries of the source manifold, and that gives you a closed surface. And then you do the path integral using this closed surface as your boundary condition. Okay, that gives you a number, and this is what we call a trace. It's not, trace in the like algebraic natural sense, but this is what we call it for now. And it satisfies trace AB equals trace BA just by looking at these pictures, right? You get the same closed surface, and you can also find that the inner product is also a trace. If you compute inner product between A and B, it's trace A star B, and it's represented by this picture here.
Sorry, what happened to the value of sources on those orange boundaries? So this is a boundary. So the orange things are sources that take values, right? In principle, J left, the left boundary, the value of J something, right?
Yeah, we need them to be matched, be the same. Yeah, because remember we took in our case we consider like the situation where these boundaries are the same, right? Including all the data.
Sorry, I'm kind of confused. The choices of J defined on this cylinder, let's take it to be a cylinder, defines the operator. So I can pick for every choice of J's along the cylinder, I have a different operator.
Yeah.
If I have a J where at this end and this end the values don't match, that is an operator. You're saying does it have a trace?
I don't define trace for those kind of operators. I only define trace for the operator that the boundary data match with each other. So what?
What do you call it trace then? If it's only defined for some operators, it's just a name. If it's a name, it's okay. But
sure,
doesn't. Yeah.
I mean, these are the only operators that we consider. I mean, the manifold is not just a cylinder, right? In between, you can have like genus or any other matter sources, stuff like that. So there are many different.
This you take your boundary. This way of saying it, if I can just arbitrarily cut it in different places because there's value J, J takes on values, all sorts of values. But and every time I cut it, I get an operator. But most of those operators don't have a trace.
Yes, don't have the trait that I just defined.
But can I think of operator as like, I'm not fixing the boundary conditions, so let's say I have some. If I wanted to compute the matrix element of the operator, I would put, let's say, JL, JR matrix element, I would fix boundary condition JL and JR, and then compute the path integral.
Yeah.
To compute the trace, I have to fix, I'm computing the diagonal elements. So JL equals GR, and that's the word. This is the way, right, way to think about it.
Yeah, you can say we only consider the diagonal elements.
J along the cylinder is labeled as operator. It's a function word. Right? So your operator is defined by function words, things along the, but it's not matrix elements or for different configuration of J, you have a different operator. Because he wants to view this as coming from some sort of, you know, quantum gravity path that on some kind of gives this.
You'll fix all the data on this kind of this cylinder. And the data you fix is required such that you know the boundary data are the same.
So this is the matrix element of the operator between the BL and PR. That's the interpretation.
The matrix, yeah. And BR and BR are the same.
The source values are 0. Are you setting them to, are you setting the trace to 0 or are you saying you can't define it? Like,
What is there?
you said that initially you could take linear combinations of these,
Mhm.
right? For example, you can say an operator, which is a linear combination of these source manifolds, each of them with the same bound, with the same boundary condition on the boundary of the source manifold.
Yeah.
Then your trace would be gluing many of these.
Right.
Combinations.
Yeah.
But in some sense, if you consider only the ones with the same boundary source, then you're sort of considering one particular basis, like get I, ra I.
Mhm.
And then you could have a linear sum of them, and then your trace will be sum of those.
Yes.
But if you think of them as having two different sources on the left and the right boundaries, it would be like get I, ra j. In which case, the matrix trace will set it to 0. If I take the matrix trace of like get 1 with bra 2, set it to 0. Okay, so here are you defining trace in the case when the sources are different, are you defining it to be 0? Or are you saying the trace sort of exists only if both these source values are the same?
Yeah, you can say it's 0. You can assign some number to those cases. But yeah, here we just don't define trace for these situations. It is very.
Yeah, suppose I want to visualize this as some word geometry model where two brains sitting at the two ends, and I have some sort of bug. If I want to visualize it like that, then am I claiming that the two brains are equivalent sitting at the two endpoints? Like the two manifolds of the boundaries, like if I try to visualize them as two brains and the bulk as some geometry or some worked higher dimensions, then am I claiming that the two brains sitting at the two ends of the two boundaries are equivalent here?
Yeah, I mean, okay, so first of all, this whole thing, this whole surface is the like boundary. It's the source manifold is the like boundary for your bulk. And here I'm just considering a very special situation where these red circles are the same.
So you're claiming them to be the same?
I'm not claiming to be the same. I'm just considering a very special situation. They're not clearly in general different. Considering the like diagonal case. Hope is clear. There are more
So
questions.
Don, you haven't argued it's a Hilbert space or anything, it's just a bunch of numbers, right? that we're
Yes.
discussing. So you're calling it colloquially operators, but these are just numbers at the moment.
Wait, these are not numbers. These are pictures. Right. If I take a trace, I got a number, right? But these are formally operators.
So operators acting on what?
Oh, I haven't told you that.
But
I will tell. I mean, if you,
are they're functions?
they are functions.
I mean, as long as it's not closed, you cannot get the number. If you have an open manifold, there is no number. Side is only closed.
But I mean, I thought this whole story started by saying that the issue I had at the beginning was that you were calling it M, but it's not just M. You also want to fix the boundary conditions of all the fields. So all the fields have a fixed value along this whole thing. Right?
Right.
So the metric at every point is fixed.
Yes.
The scalar field at every point is fixed. It's not up to us to change it. You fix this and you take a chunk of this and that's a number.
No, but no number. What number?
So you just called it zeta of.
No, but that's only for closed. If you have boundary, there is no number.
I thought it was.
Well, but you can fix some different set of data and with some other operator, right? I can say it is some other number. But
No,
here,
but there is no number associated with that. As long as there is a boundary, there is no number. The number is only for a closed manifold.
right, that's what said. When you take the trace, you get one
Then
number.
you,
When
if you follow with
minima,
that, there is no number.
minima is saying, okay, you have lots of numbers that is specifying the data on this surface.
That's what I was asking at the end of the whole thing. Just I'm confused about what is the number we're associated to this. Because you wanted to say that, okay, whatever. Oh, okay, no, I'm not sure.
Okay, I don't associate any number to this at this moment. It's only I only associate numbers to the closed surfaces. That's clear. Okay, and I mean here I define some kind of some algebra, and to define algebra you don't need some Hilbert space, right? You just need the multiplication, and it's closed under multiplication. But then I will talk about how this algebra is represented on some Hilbert space. Okay, this is the trace. Okay, maybe before I do that, I will talk about a property of this trace, which we call the trace inequality. And the proof is based on the reflection positivity condition. So here I'm considering four boundary Hilbert. So before I tell you that the space I consider only has two boundaries, but you can consider a larger Hilbert space where you embed these two boundary, sub Hilbert space into that Hilbert space. And now you consider two states, right? The first is this. So if you want to look at the thing below this blue dashed line, this is a state. Which I labeled by this. So the four boundaries are labeled L1, R1, L2, R2. And I also consider this kind of this states, below this line. So A and B are just two different surfaces in general with different data possibly. And first, okay, we compute their norm. So the norms are the same. They are computed by these two pictures respectively. I think this should be A and this should be A star. And you can use the same number. So what you get is trace A star A, trace B star B, right? For these, you can just look at these pictures. And here I use this factorization axiom that I mentioned because you want to think of these two pictures as two independent traces, basically two independent path integrals, and we are kind of excluding the possibly bulk wormholes that could connect these things. So that's where we use this axiom. And okay, so this is their norms, and we can also compute their inner product by doing also this kind of gluing. And their inner product is given by this. If you just track along these pictures, it's trace BA star and B star. And because of Cauchy-Schwarz inequality, right, the inner product is smaller than or equal to than the product of the norms, something like that. You get this trace inequality. This is one thing we proved using this reflection positivity. Another way of saying it is that the difference. So you consider state that is the difference of these two states, and you require the norm of this state to be positive definite.
Yeah, I'm very confused. You have a vector space. What is a vector space? How do you define it?
Well, I have a Hilbert space, right? Because if you remember, I defined the Hilbert space before. The inner product is defined by the gravitational path integral, right? So
when you draw this cylinder,
yeah.
right? You want to say that's an operator, right? What space would it act on?
Okay, so later I will tell you it acts on the two boundary Hilbert space. So where the states are, that's these guys. Does that make sense? So here first I talk about the Hilbert space, right? These are the states. And okay, later I will tell you these are also operators, and the operators act on this Hilbert space. Does that make sense?
Maybe.
Oh, okay. Sorry if it's confusing. Right. So at this step, I haven't talked about the how the operator acts on the Hilbert space yet. I'm just using some observations that the states can also be thought of as operators, and there's some relation between the inner product and the trace I define. And using reflection positivity, I can derive this inequality here. And okay, now I will talk about how the operators act on Hilbert spaces. So for some surface A, that is these source manifolds with two boundaries, two red circles, you can define left and right operators, with their actions on this Hilbert space. So for each surface, you can define two operators. You can either act this on the left and act this on the right. Okay, and they're acting using different multiplication rules, which I write here, but it's not super important. You just need to know that there are different actions, left and right, and we can actually prove that these operators are boundary, because from the trace inequality we proved before, here. Okay, so the left-hand side can be interpreted as this, right? And this is bounded by trace A star A times the norm of the state B. Because if you remember from our axiom, we assume the path integrals are finite, right? So this trace is finite, which means that the operator norm of the such operators is bounded by a square root of this trace. Okay. And the same works for the right operators. Right, and also these operators also, you can also extend the map trace that we defined earlier to this representation, right? What we just defined to be the same as the trace of in the surface algebra. Is it clear? And now, we define two commuting algebras, a left and a right of bounded operators, but they're not von Neumann algebras yet. And we can actually complete them under the weak operator topology to von Neumann algebras, the left and right von Neumann algebras. And it's the same as taking the double commutant to do the completion. Because we have the Hilbert space, and we have bounded operators, so you can do that. And we now want this map that we called trace earlier to be an actual trace on the Von Neumann algebra. And for Von Neumann algebras, the trace only needs to be defined on the set of positive operators. And so it's a map like this. They can map positive operators to some number, 0 and infinity, including infinity. And by positive operators, I just mean operators of this form. But you know, in Von Neumann algebras, there are many operators that are limits of some other operators. For example, in our case, this Von Neumann algebra does not only include these surfaces, but also limits of surfaces, right? So the trace that we define pictorially might not work in these limiting cases. So we need to define it in some other way. Right, how many times? Right.
We have time.
Okay.
I think after switch it for 30 minutes. Continue.
Oh, okay. Been a little slow. Yeah. So to define trace, we are going to use the one family of operators, which is the cylinder operators. So these are just defined by the manifold with like this. There's some lower some d-1 dimensional manifold across some interval, so they are cylinders with length beta. And we can also define the corresponding cylinder state C beta. And in ADS-CFT, you should just imagine them as e to the minus beta h Euclidean time evolution operators. And we can prove following properties, how they multiply, and the operator norm of C beta is 1 in the limit beta goes to 0. And this is, yeah, we can prove this, and intuitively you can just think of this, beta goes to 0 limit of C beta, giving you the identity operator, because it's like you do nothing on the state, you glue a small cylinder and you shrink the length to 0, just basically do nothing. So that gives you the identity. And we also proved another property, which is monotonicity. So first of all, we define a normalized cylinder operator, that is the cylinder operator divided by the operator norm. And then we can show that this thing is monotonically decreasing under increasing the length of the cylinder. Okay, and this actually help us to give this new definition of the trace, because so first of all, we can define trace of some operator as the limit of this thing. So this thing is represented in this picture here. So you just sandwich this operator with 2 cylinder states, and then you take the length of the cylinder to 0. Right. So effectively, this is gluing the 2 ends of the operator, and it agrees with the old trace for operators that are, in this algebra, not the Von Neumann algebra, despite our axiom of continuity. Okay. And also because of this monotonicity property we proved, this trace can also be written as a supremode, because sometimes the limit might not be very well behaved, but the supremode is well behaved. So this is our new definition of the trace, and we can extend this trace to all positive operators in the Von Neumann algebra. Okay.
So when beta goes to infinity, that would project over the ground state if you put a very long cylinder.
Right.
But how you see what the, I don't know if that's something you want to see.
Yeah, I'm not sure what we'll get in that case. Yeah, here I'm considering the beta goes to 0 then.
Yeah, but you also take beta to infinity. Yeah.
That's true.
H is mounted, like. So C beta is always beta 1.
So sorry, what was that?
C beta is like less than one in some way.
It's less than one.
Like,
Yeah, sure. It's e to the minus beta. Yeah.
So I guess that's why you have the monotonicity.
Yeah, that's kind of the intuitive way. Yeah. Yeah, I'm not sure if beta goes to infinity limit and gives you interesting. Yeah, I haven't thought about that. But, okay.
Are we still in the B sector?
Yes, yes.
Still in this sector.
B, yeah, or like B union B sector. Right. Yeah, so these red circles are just the B boundary. Yeah. Yeah. Right. So we can also prove the cyclicity for this newly defined trace, and also we can prove the following properties of a trace, which is faithful, normal, and semi-finite. So faithful just means trace A is zero only if A vanishes, and normal is some kind of continuity statement of the trace, and semi-finite means you have some, sensible trace that measures the kind of size of some operator and doesn't assign infinity to every operators. And so these three are very important properties that for a trace in von Neumann algebra. And the last thing is the trace inequality. We proved this for the surface algebra before, but now, but we can prove this for the entire von Neumann algebra, for operators in the von Neumann algebra. Right. So, okay, I'll be quick and talk about the structures of the von Neumann algebra. So, first of all, every von Neumann algebra can be written as a direct sum or integral of vectors. Vectors are algebras with trivial centers. For type 3 vector, there's no faithful, normal, and semi-finite trace. So our algebra does not contain type 3 vectors. And for any such a trace on type 2 vector, you can always find a non-zero projection with arbitrarily small trace. But from the trace inequality we proved here, if we take both A and B to be a projection, and what we get is, unless trace P is zero, it is always bounded below by 1. Okay. So this excludes the type 2 vector. So our von Neumann algebra can only contain type 1 vectors. Okay.
Sorry, can you go back?
Yeah, sure. Okay. We can also prove that it must be a direct sum, not integral of type 1 vectors. This is because if the spectrum has some non-discrete part, we can use it to construct a projection that is less than 1. You can, for example, if you take some like interval of this spectrum, you can always look at the smaller part of this spectrum and it gives you a projection with smaller trace. So which violates the bound on this trace of projection. So that's why we have a direct sum of type 1 vectors. So here I just list some more structures we find in our paper. So first of all, AL and A right are commutants of each other, and they share the same centers, and their decompositions are labeled by the same index set. This, right, and note that this AL and AR are in general different from bounded operators on the Hilbert space of the B sector Hilbert space. So what I mean is that what algebra you get depends on the representation. So this Hilbert space is just the Hilbert space with one boundaries. For example, you look at this picture here. Although you have the same set of services that you use to define the algebras, but the final von Neumann algebras you get are in general different. Okay, and yeah, because our algebra only contains type 1 vectors, so the two boundary Hilbert space can be decomposed into this into a sum over super selected sectors, and in each sector you have a factorizing Hilbert space. Right? And you might ask that it doesn't factorize because in ADSMT we would expect we only have one such super selection sectors, and the two boundary Hilbert space should factorize. So this is kind of a contradiction, but this is the structure we got from the axioms that we assume. And it would be great to know what kind of axiom you could add to get only one sector. I mean, when it means that the whole Hilbert space factorized. Okay, and in general, there's one sector that is the tensor product of one boundary Hilbert space. So for some value of mu, it looks like this. So so this is just one boundary Hilbert space cross one boundary Hilbert space, and the states should look like this. So these are like disconnected manifolds. But in general, for other types of mu, you have connected manifolds, but somehow you can also write these states as some factorizing states. Okay. This is here. And then I will talk about the normalization of the trace, because we know that the trace is the fifth-fold normal semi-finite trace is unique on a type 1 factor, but in different for different type 1 factors, because in our case we have a sum over different type 1 factors, the trace might be different. The scaling of trace might be different. So in general, you should have this kind of structure that if you restrict to some Hilbert space mu, this is the relation you get where trace this big trace mu is the standard Hilbert space on this this small this sector, right? And trace inequality gives that trace P is bigger than or equal to 1. And if you set P to a projection to this single mu sector, you get that the mu must be bigger than or equal to 1, right? But we actually found a stronger statement saying that the mu is a positive integer. The main idea of this proof is that we embed this two boundary Hilbert space to two n boundary Hilbert spaces, and you consider states like this. Okay, so first of all, so in this two n boundary Hilbert space, there are two n boundaries, and you want to connect these boundaries using the projection operator. Remember, operators are also states, right? So you can do this, and this is some way of connecting these boundaries, and then you do a permutation, right? There are many kinds of permutations you can do to get different states, and depends on the permutations, you multiply by this vector, and you form this linear combination. So this is like a generalization of what we did when we proved the trace inequality. There we only have 4 boundaries, and we consider the AB states and their permutations. And here we're considering 2 n boundary states and form a state using this kind of permutation. And you compute the norm of this state, and it turns out you get this. So any non-integer trace P would violate the reflection positivity for some n. So if you want to reflect some positivity for any n, the trace P must be an integer. Okay. So that's the proof. And excuse me, because the trace n is the trace P is the integer, right? So which means is that the mu is an integer, right? And we could interpret this result as that there's some hidden sector of the Hilbert space there, and the path integral is not only counting the degrees of freedom of the original Hilbert space, but it's also counting some degrees of freedom in this hidden sector, right? So this is just some interpretation we have. It could be that these Hilbert spaces has some hidden sectors, and the Hilbert space trace on this extended Hilbert space matches with the trace defined, from the algebra using path integral. Okay. This is some interpretation. It's not, we're not clear if there are, examples that this really happens. Okay. So maybe in the end, I'll give you some example of this this kind of structure. So the first example is GT gravity. For GT gravity is it's special because there's no like one boundary states. All the states. So first of all, in GT, when you do the path integral, the boundary conditions are just given by circles with some length beta. And if you're cutting it open, you always get, two open ends, right? And some line element connects between them. So those are the states of GT gravity. And these are two boundary states, right? So you only have two boundary states, and in this two boundary sector, all the left or right operators are line elements with length beta that correspond to this operator. So you can do time. The only operator or the only set of operators are bounded functions of the Hamiltonian, right? So it turns out that the von Neumann algebras are actually abelian algebras defined by these operators. And because all the operators commute, right? They are all in the centers. So you can decompose the Hilbert space using the eigenvalues of the center, and the index mu I mentioned before can be taken to be the energy E, right? And the two boundary states are labeled by this. And in pure JT is actually the trivial that the energies on the two sides must be the same. And it's also true because each sector is only one dimensional. There's only one E here, right? And we have shown that E must take discrete values because we've shown that the algebra is a direct sum rather than the integral of type 1 vectors. And there are some story about GT gravity due to ensemble of random matrices, and for a single matrix in this ensemble, the energy spectrum is indeed discrete, which is consistent with what we have here. Okay. So maybe I will not talk about this example. Okay, but yeah, maybe I'll just talk about the entropy of this algebra. Okay, right. If we have some two boundary state psi, like say something like this, we can get the density operator for the left boundary by doing this. So this is just psi star. So if you look at the piece over here, this gives you the density operator, and then we can define the von Neumann entropy by this, right? And this is a trace we define. And because in our case we have different sectors, so this density matrix also have some decomposition into these sectors, and the entropy can be written like in this way. right? This is the usual story where we have some average over von Neumann entropy in each sector and some entropy of mixing term. Another way of computing the von Neumann entropy is that you do the replica trick. So you first compute the linear entropies like this, and then you take n goes to 1 limit. So for example, this picture, I'm computing trace rho to the third power. By doing path integral using this boundary condition, you get the linear entropy, and take the n goes to 1 limit, you got the von Neumann entropy. Of course, we're assuming some, you can actually do the analytic continuation. But what is important here is that in the gravity case, in the semi-classical limit, this kind of thing is done by Lorentz and Monsignor, and the von Neumann entropy they got is the Takanagi formula. So in some sense, our results provide a bulk Hilbert space interpretation of the RT formula, because on one way you can you got RT by doing this kind of path integral, but on the other hand, this von Neumann entropy can be also written in terms of things related to this bulk Hilbert space we constructed. So that's thing we have here. Okay, maybe I'll say this slide and then go in. Yeah, so the last thing I would say is that when our axioms are violated, because in these recent papers, people get type 2 algebras instead of type 1 in the semi-classical limit, and what goes wrong, right? In our story that that could destroy our type 1 algebra. So the thing is, in general, for gravitational theories, if you do the path integral, in general, there's some parameter e to the s naught, such that this path integral goes like e to the s naught. And the semi-classical limit corresponds to the limit where you take this number to infinity, right? And if you want a well-behaved, semi-classical limit, what you might do is you rescale the path integral by e to the minus s naught, and you get a final answer in that limit. However, if you do this, the factorization axiom is violated, because on the one hand, you have one path integral, and on the other hand, you have two path integrals. So the two sides are rescaled differently. So in the end, if you use this theta tilde as your path integral, you get some extra number here. And if you take s naught to infinity, this factorization is actually infinitely violated. So in some sense, the factorization axiom also gives you some preferred normalization of the path integral. And also, another thing is that the trace inequality we proved, remember that this inequality is essential for our type 1 algebra, should be modified to this, right? On the right-hand side is you have some extra vector here. And if you take this vector to be infinity, then this inequality becomes trivial. It doesn't give you any constraint on the algebra, so you don't get type 1. And if we have large but finite e to the s naught, we should expect the type of algebra to be approximately type 2. But we don't know how to really show this, but we should expect this to in accordance with the recent papers.
But type 3 is still not possible because you have trace.
Yes.
Right.
Right. Yeah. Yeah, that's right. Okay. Yeah. Maybe I'll just leave the summary and questions here, and here we have some out of time. So thank you very much.
Any questions?
seems like major part of. The thing that played a major part was the traceable equality, right?
Yes, it's very important, right?
And that came from factorization
Uh,
and Cauchy for the source, right?
yeah. Reflection positivity and factorization.
So you mentioned like one validation of factorization, which is using this e to the s naught part.
Mhm.
And if I forget that thing and just answer, if I don't require factorization or if I weaken that, can I still derive trace inequality or something like that?
I don't know. You certainly can't use the way I derived it to